Okay, we're going to begin our section on applications of the derivative with something called related rates, and it means just that, rates that have some sort of relationship. Rates of change to us mean derivative. So if a variable depends on time t, then its derivative, let's say we have y, we have some function of y, and we want to know the rate at which it's changing with respect to time, then that's going to look like dy dt. And we could have dx dt. Let's say we're talking about the volume of some container and we want to know the rate at which the volume is changing with respect to time. The rate maybe at which the area is changing with respect to time. All of these are called time rates of change, and a rate of change is a derivative. So we recognize that as Leibniz notation for the derivative. So when we have related rates, we're going to start out with a related equation between two different variables. So in a related rates problem, the idea is to compute the rate of change of one quantity in terms of, or given the value of, the rate of change of another quantity. And I know that sounds, a little confusing, but we're going to do lots of examples so you'll understand what that means. So if we have, let's say, the volume of a sphere related to the radius of the sphere. The volume of a sphere is 4/3 pi r cubed. Well, there is a relationship between the volume of that sphere and the radius of that sphere. The relationship is the bigger the radius is, the bigger the volume is going to be. Or the smaller the radius is, the smaller the volume is going to be. Well, we're going to take that relationship between these two variables, and now we're going to talk about, is there a relationship between the rate at which the volume of the sphere is increasing or decreasing? Is there some sort of relationship between that rate of change and the rate at which the radius is changing over time? Related rates are always time rates. So when I say the rate of the change of one quantity, let's say the rate of change of volume, in terms of or given the value of the rate of change of another quantity. So those are the kinds of problems we're going to be doing with related rates. Since our functions are going to involve volume, area, horizontal, vertical measures, and so forth, we'll have to use implicit differentiation, differentiating with respect to time to find our rate functions. Again, don't obsess about that making 100% sense at this point. We're fixing to work a lot of examples. So there are a wide variety of time rates, but many comparisons can be made to help with setting up your problem. The best way to learn the process for solving a related rates problem is to work examples. So that's what we're going to do. We're going to work example after example. Please take good detailed notes. Follow the overall process, and you'll see the repeated process that I do in each one of these examples. All right? And our process is going to involve drawing a picture, drawing a mathematical model, coming up with functions and relating one part of the problem to another part of the problem, and then implicitly differentiating with respect to time and so forth. So here's our first related rates problem. Air is being pumped into a spherical balloon, that means something, so that its volume increases at a rate of 100 centimeters cubed per second. How fast, that's a rate, is the radius of the balloon increasing when the diameter is 50 centimeters? So it looks like a fairly simple little problem, but there's a lot of information just in these couple of sentences. All the information I need to answer this question. So air is being pumped into a spherical balloon. Well, there's one model for a sphere, and there would be the radius of the sphere. I don't know if you had to draw models of spheres in geometry or not, but that's kind of a two-dimensional take on a three-dimensional object. We're pumping air into this spherical balloon. So air into the balloon lets us know that the rate at which the volume is changing, that's what the volume increases at a rate of. This is how I would write that. This is the rate of change of the volume with respect to time, right? That's what that means. And it tells me that it's increasing. Increasing means is getting bigger. If it was decreasing, I would put a negative sign there. At a rate of 100 centimeters cubed per second. So there's a rate that they've given me. They gave me the rate that the volume of this spherical balloon is increasing. How fast is the radius of the balloon increasing? At what rate, how fast is the radius of the balloon increasing? This is the rate at which the radius is changing with respect to time. So over time, intuitively we know, over time, if we're pumping air into this spherical balloon, the balloon's getting bigger and bigger and bigger, which means the volume of the balloon is increasing, and which, if the volume of the balloon is increasing, we can tell from our picture here that the radius of the balloon is going to have to increase as well. So they haven't really told us what the volume was or what the radius was. They've just told us the rates at which things are changing. They gave us one rate, and they're asking us to find a related rate. They give us one more piece of information. They want to know specifically what the rate of change of the radius is when the diameter equals 50 centimeters. So now we have to find a way to relate the volume and the radius of a sphere. That's where geometry comes in. We remember from geometry, and if we don't, I have a handout that I can give you if you'll ask for it, that has all of these geometric relationships of, different types of three-dimensional or two-dimensional geometric figures. The relationship that relates the volume of a sphere with the radius of a sphere is this relationship right here. It is always true, no matter what the volume and the radius are. If we're in a sphere, the direct relationship is the volume will always be 4/3 pi times the radius cubed. Well, if that's the relationship in a sphere between the volume and the radius, how can I find the related rates of that? We have volume equals 4/3 pi r cubed. I need a way of relating dv dt with dr dt. And I know a relationship between the diameter and the radius of a sphere. Telling me the diameter is 50 centimeters is the same as telling me the radius is 25 centimeters. So here's where, once we find what the relationship is between the rates in question, we are always going to implicitly differentiate with respect to time. Now, we could differentiate this with respect to r, with respect to v, but we're going to differentiate with respect to time. Why? Because the volume and the radius are changing over time. So we're always going to implicitly differentiate related rates, all related rates. You're going to implicitly differentiate with respect to t. So what was the process for implicit differentiation? It was term by term. Take the first term, differentiate it with respect to time. Copy down any equals or pluses or minus. Pop your constants out front. Everything that we know about derivatives up to this point still holds true. Now we're going to implicitly differentiate r cubed with respect to time. That requires the chain rule. Remember, the chain rule says it's the derivative of the outside, not changing the inside, times the derivative of what's inside. Well, for us, we want the rate at which r is changing with respect to time. So let's clean this up a little bit. dv dt has to equal, let's see, this 3 and that 3 will cancel. So 4 pi r squared times dr dt. And this is the related rate. And we got it from the relationship between a volume and its radius in a sphere. And we implicitly differentiated, and now we know the relationship between dv dt and dr dt. It is right here. Now we're ready to actually answer this question, because I have a value for dv dt, and I have a value for r. If I plug those values in, then I just have one variable left. And lo and behold, that's the variable I need to solve for. Let me get rid of some of this so you can see the work a little bit. I've run out of space, but you just keep going down on your notes. You can write this below. So dv dt is 100 centimeters cubed per second. And I have 4 pi, which is a real number. Nothing wrong with 4 pi. And r is 25 centimeters. And now I want to solve for dr dt. So here's my variable. So I'm going to take everything that it's multiplied by, and I'm going to divide it on both sides. So dr dt, I'll come over here where I have some space. Dr dt has to be 100 divided by 4 pi times 25 squared. Now, what are the rates on dr dt? We know that this is centimeters cubed per second. So we have volume, which is centimeters cubed, and we have time, which is second. So here we have radius. That is the measure from the center to the edge of that sphere. That's in centimeters. And over time is per second. So there's the right units. Now you could clean this up some more if you wanted to, but you don't have to. That's a perfectly well-defined, good answer. Now the one last thing that I want to hit home before the end of this video is that when we are asked in words, we answer in words all the time for our word problems. And related rates aren't the only word problems we're going to have. When they ask us in words, we answer in words. So the answer to this problem is the radius is changing at a rate of, we could clean that up if we wanted to. That's going to be 25. One of that's going to cancel with one of those 25s. So this is actually going to clean up to 1 over 25 pi centimeters per second. And specifically here, I wouldn't even have to use changing. I could say is increasing, because that's a positive value. There is our first related rates problem. You'll see when we start the next video, the same type of process will be used on all of these related rates videos. So watch for the next video. We'll do some more examples.